Okay, so this is all fine, and it's actually very cool, and of course I'm really proud of this. But the question is, what's the cost, right? It's okay to sort of spend zillions on things in a public sector research lab if you have them. Can that really be an approach for real-world use for industry, etc.? And traditionally, formal verification has a reputation of being really expensive. So I'd like to have a look at what are the actual costs of this kind of verification. So cost of assurance. From this proof chain, how much effort did we spend in the various bits? The big thing, and I said this is the biggest or second biggest proof ever, was the refinement from the abstract model down to the C code. And in this we invested 21 person years. So that's a significant amount of work. The project went over 4.5 years, but if you're honest and think about research projects that go over 4.5 years, very few actually invest less than that. So that's not an unusual number. How about the other bits? And this is really the good news. Turns out, by having done this formal refinement from the abstract model down to the C code, everything else becomes really easy. So integrity was shown in 4 months with a total effort of about 1 person year. And this was a degree of assurance never reached before for any kernel. There's no such sort of integrity proof before that goes down to the C code level. And having done the functional verification, we could do it in a year. Confidentiality was a bit harder for the reasons I explained. It requires far more work. In particular, we had to develop a form of non-interference which is preserved by refinement, and that included, among others, to lift the abstract spec, or to have a different version of the abstract spec that was completely deterministic, because any non-determinism could introduce a channel. So it cost us 4.5 person years, but at least half of that went into developing new techniques. So what in the company we call the non-recurrent engineering cost was actually only about half of that, not reusable. Availability came for free because of the construction of how resource management works in a kernel and using the other properties. And the refinement from C code down to the binary was about 2.5 person years, but that was just an investment in tools, so that's completely reusable.
What it means availability, formally speaking?
Availability means that your access to resources is independent of what other parts of the system do.
So it's in particular deadlock freedom?
No, because that's not an availability issue. Deadlock free, I mean, the kernel is deadlock free, yes. But of course you can produce deadlocks at a higher level. Availability means that your ability to use resource in the system is not impacted by what other parts of the system do. So if you're living in your partition, you can you can manage your resources independent of what other partitions do. Which is not the case in any operating system I know, by the way, any other. And the timing analysis was also about 2 person years, which also went into tools. So compared to the refinement from the abstract model down to the C code, everything else was really cheap. So what about this cost of 21 person years? That sounds a fair bit for verifying a kernel of about 9,000 lines of C. Turns out this translates in about $400 per line of code. The exact best figure we have is 372, but that's close enough to $400, and it's not really that an exact science anyway. And we estimate that we can reduce that by a factor of 2 if we did it again. So this is new territory, right? We've written kernels before, but we've never verified a kernel before, and therefore there was a lot of learning involved. And remember the number I mentioned earlier for cost of high assurance software? Does anyone remember? $1,000. So we're actually looking quite good here, right? It's probably somewhat an unfair comparison because our people are cheap. If they did the similar thing in industry, they would be paid at least twice that. And the people who do this for $1,000 are probably not as good as ours in the first place. But anyway, I mean, this is a really good starting point. Still, why was it so expensive? 21 person years for just 9,000 lines of code. Part of the answer is this. That's the call graph of SEO4. And it basically shows you a high degree of messiness. It's almost completely interconnected. And this is typical for microkernels. Microkernels, they have they may have an internal structure in the sense that there's sort of modularized functionality, but in the end, everything is interconnected. My tongue-in-cheek definition of a microkernel is you take an operating system, pull all the easy bits out, and the black molasses left is your microkernel, and this is sort of represented in this figure. What this tells you is that proving any global invariance is going to be really hard because of the degree everything interacts. And it turns out 80% of the effort went into proving invariance. And so that's basically when any change happens is the scary question, does it affect any of the global invariance? Because if so, then reproving it means it's lots of work. If it doesn't, then it's easy. So the breakdown is also interesting. The original design, so this is in Haskell prototyping the spec, was 2 person years. So a lot of effort actually went into coming up with the right model for the kernel. And remember, we've built 2 generations of microkernels before, so we had a clear idea of where we're heading, and still we invested a lot of effort into coming up with the right kernel model. The C implementation, 2 months. As a matter of fact, the first version was done in 2 weeks. And this was off the Haskell implementation that was done in a weekend. It got refined, etc., over time, but still that's actually a very small fraction. And compared to other people building microkernels, which do basically just stay in C and don't think about verification, they would typically invest a much higher proportion of their time in writing the C code. Debug and testing, almost non-existent. That was by design, right? Why would we test it? We prove it correct. So we let some poor undergraduate students loose on it, and that was a degree of testing. Kernel verification, 11.5 person year. So this is the real heavy bit. And local formal frameworks, 9 person year. So that's basically half went into the actual verification of the kernel. The rest mostly in frameworks, and of course these are completely reusable. So if we did another one, we could still use those and we'd only have to redo that bit. And as I said before, we estimate we'd probably be about a factor of 2 more productive doing that. So this is why we estimate the repeat cost to be about 6 person years. And then it becomes really attractive. Because traditional engineering, and this is based on actual microkernels people did with similar background experience. So there's this pistachio microkernel, which was built at the University of Karlsruhe about 10 years ago. From, again, people who knew what they were doing. They built kernels before. So a very comparable exercise in the sense it was a comparable piece of software, a kernel of a similar functionality, basically same inheritance, people with similar background doing a kernel, and they spent 4 to 6 person years doing that with traditional methods. And we estimate we will spend 6 doing a formally verified one again. In other words, for this kind of system, we think formal methods are actually cost competitive. And to me, that's the probably most unexpected, but certainly most reassuring and impressive result of the whole thing, that we can actually do things right without being more expensive. And to me, that's really sort of the foundation for ongoing research agenda, trying to build complete systems that are verified. Yes?
When you say the formal frameworks are reusable, what exactly does that mean? If you were to build a very different microkernel, what would be the reusable part?
I don't think there's such a thing as a very different microkernel, actually, because any good microkernel looks very much like an L4 microkernel. It means that if you wanted to verify a compiler, but that's true, right? If you look at, there's lots of microkernels around, they're much more popular than you think. Basically, any safety critical software that actually has operates on a processor with dual mode execution and protected mode, you will find it's a microkernel. But they are either really slow, basically first generations, or they are clones of L4. Trust me. So if you wanted to do another microkernel, it would look very similar in many ways. If you wanted to verify a compiler, then I'm not sure how much of that would be reusable. Okay, so the numbers, if you look at different papers, the numbers slightly differ because we've done stuff afterwards. So this is just a disclaimer. Typical question, did you find any bugs? Have a guess.
Yes.
Okay, how many? Okay, you guys are optimists. So this is the shallow testing we did before. As I said, if we wanted to build like a real commercial grade system, we would obviously invest far more time in testing, etc. And so our testing was let a few students loose on it, poor suckers. That revealed all of 16 bugs. Formal verification revealed 460 bugs. And the breakdown is interesting. It's about a third in C code, design and specification. So specification bugs is where we revealed during verification that the specification had different properties from what we wanted. So that we class as a specification bugs, and we fixed that. So changes to the specification because verification showed that the properties are different from what we expected are specification bugs and got changed in the spec. Design, so this is like the intermediate representation, the executable kernel level, where we found about 130 bugs and then 160 bugs in C. So pretty much the same bug density or the same number of bugs in all three levels of abstraction.
Quick question. So when you find a specification bug, do you just have to change the specification, or does that entail some modification in the design afterwards?
Obviously it does, right? I mean, if you change anything at top level, it needs to trickle down. And some of these are very invasive and require a lot of work. So the earlier you find them, the better. Which is also a reason why we did put a lot of effort into verifying the step between the formal spec and the executable model, and kept that as low level as possible because it's revealed most of these issues.
Did you find any bugs that have been that are not real bugs just because you made an abstraction? So when you abstract, you introduce extra behaviors that are not behaviors of the real system. So how many bugs of this type you have found? Typically, when you produce abstractions of software, you have many, many bugs of this type.
I'm not aware of any. I would have to ask, but I would be surprised if that was an issue because the specification wasn't written in a vacuum. And the actual approach we took wasn't actually top-down. As sort of from what I've said before, you could assume that we use a top-down approach. We didn't. We know that you can't build a decent microkernel using a top-down approach. We actually used a middle-out approach. So we really started at the executable spec and made this as low level as possible to capture as much of the actual kernel functionality as possible, and then abstracted from that the abstract spec. So probably by construction we excluded those.
I doubt, because you may introduce non-determinism and you have a more extra behavior in the abstract model that you may not have.
Yeah, it's possible, but I've never heard of an issue like that, but I was not involved intimately in any little detail, so I'd have to ask that separately, but I'll follow that up. Okay. Yep.
The specification bug, did you find any bug which forces you to revise the specification such that you were having requirements which were in conflict, or you had to give up some of it?
I'm not sure whether there were any conflicts in the specification. This is again sort of consequence of the way microkernels are constructed, in that the API is pretty orthogonal. Plus also remember what I just said, that the spec was actually extracted from the model. So we went from the executable model up to the spec. I don't think that was an issue. I mean, the specification bugs were mostly corner cases which were not clearly thought through, and which were exhibited by the specification. And there was one case where there was basically the system lent itself to a very easy way to construct highly unsecure system, which we didn't have intended, and that got fixed up in the spec. It didn't make the system automatically insecure. You could still use it in a secure way, but it was unnecessarily hard to do so. So that's a specification bug in the sense it was a property which we didn't want. Okay, so let's put this into context. I already said high assurance, rule of thumb, 1,000 lines of code. This is a bit apples of oranges comparison, because the $1,000, they include testing the hardware, etc. But the bulk of it really goes into the software. And of course, there's no guarantees from those processes. They're very process-oriented. COM criteria, which this is based on, is essentially a glorified ISO 9000 thing. It's very much based on dead trees and software process and all that crap. And of course, the other thing is, and this is really, I suspected that for a long time, and then when I was with my company Open Kernel Labs, which marketed a predecessor of SEL4, we didn't get to test our competitor products, but of course our customers did, and we learned from our customers exactly what I thought, that all these other systems out there, they're highly unoptimized. Their performance is way worse than SEL4. And that comes down to the brittleness of this traditional assurance approaches. They can't really afford to optimize the hell out of the code as we can, because we know as soon as we've proven it correct, it's fine. Whereas they don't want to take that risk. So the opposite is low assurance, and this is basically numbers taken for a comparable system, in particular the pistachio kernel, where you're looking at $100,000 to $200,000 per line of code. With rule of thumb, expect $1 to $5 per 1,000 lines of code, and you can optimize it. And we are in between cost-wise, but basically in terms of performance, etc., as good as the low assurance or no assurance case. And we estimate we can improve the cost by a factor of 2, which would really make us competitive there. Yeah. So the interesting lessons from this is, compared to one of these commercial separation kernels like Greenhill's Integrity, I don't think Greenhill's Integrity has bugs just because it hasn't been completely formally verified. They actually did a degree of formal verification there. They verified isolation properties on a low-level model of the kernel, but of course the corresponse to C was done by informal methods. They're probably secure. The difference is, A, we know we are secure. We actually have proof. We probably did it at significantly below their cost, and what we really have is the security that our kernel adheres to its specification, and this is the real core properties for them building complete systems and heavily leveraging formal methods for building the complete systems. They have a formal model. Greenhill's has a formal model of their kernel. They can use that for reasoning formally about systems they build on top, but then really never know for sure that in every corner case their formal model captures the behavior of their code. And this is the really significant degree of assurance we get over anyone else. So my takeaway of this is, for the cases where traditional methods still work, we are cost competitive. We actually verified a bigger system than the traditional approaches did. The Green Hills kernel is about 4,000 lines, ours is 9,000 lines, mostly because we are more general and better performance. But also, we learned a lot enough from this that we believe we can scale this thing up. And my target for the next 5 years is 2 times cheaper and 10 times bigger. So with reducing the cost per line of code by a factor of 2 and increasing the amount of verified code by a factor of 10, and this will be a real qualitative change that allows us to do completely different things. And I'll give you a bit of a glimpse in the remaining half hour or so on how we are tackling this. Fundamentally, it's by combining theorem proving with synthesis and high-level languages, especially domain-specific languages. And fundamentally also, this is about tackling full systems, right? We basically killed off the kernel, and now we want to build complete systems. The kernel is the main building block. But the aim is really real-world systems which have millions of lines of code, of which somewhere between 10 and 100,000 lines of code are critical if you structure the system well, and the assumption is we can structure the systems in that way and verify the critical bits and thereby be able to make guarantees about the safety or security of the whole system. And we've got a really nice, and the approach is, of course, componentization, right? We structure system in components, identify which components are critical, which are not, how they interact, and then map this onto SEL4 and map the isolation requirements into SEL4 partitions and do as much of that automatically as possible. And we got a really nice driver for this, which really allows us to get towards sort of the real-world system thing. And this is this DARPA project called SMACM. SMACM is our sub-project of this. So there's this DARPA HACMS program. HACMS stands for High Assurance Cyber Military System. Doesn't matter what SMACM stands for. It's a reverse engineered acronym because it sounds nice. And the idea is to produce an autonomous vehicle with provable safety guarantees. And they're pretty serious about it because they pay a red team to basically try to find holes in the system. So their whole job is to try and shoot it down. And the project has 2 vehicles. One is a research platform and the other the military platform. So our research platform is this what we call the SMACM copter, which is a modified Ardue copter. So the Ardue copters, you can buy them for $500 or so in the store. They're called Ardue copters because they have an Arduino as a processor board. We're actually removing that, so it's no longer an Ardue copter, and replacing it up by our own A15 based processor board. Well, I'll get into that, actually 2 processors. And this is the system where we basically completely re-engineered together with our partners, Rockwell Collins, Boeing, Galois, and University of Minnesota. We built a complete software stack with the aim of making safety proofs for the overall system. And the basic safety requirement is the enemy, that is the red team, must not be able to divert the system to a point where they could capture it. And then there's the military platform, which is a autonomous helicopter built by Boeing, and the technology will be transferred on that to demonstrate that it's actually useful in a real-world sense. So structurally, this is what the SMACM copter looks like. The 2 processor boards. The first one is the mission board, so this is basically the brain of the system. It contains the critical control and communications infrastructure that directs the vehicle, makes it fly to waypoints, perform its mission of taking videos and whatever. And it runs on an ARM A15 processor. The A15 is the latest generation of ARM processors that has hardware support for virtualization that makes it easy for us to run untrusted virtualized systems on it. So in particular, we'll have a Linux system in there, which has some functionality, but we consider it untrusted, so it's used for image processing. And untrusted means we assume it will be compromised. And in the unlikely case that the red team doesn't manage to break in, we'll give them a root shell on it. So we will definitely have the enemy on the platform. And then the job of SEO4, of course, is to keep the rest of the system, the critical functionality, safe, which is this control and communications software, which will be provided by Galois and Rockwell Collins. And in order to support it, we'll need access to devices. So we'll have device drivers, which we'll verify, and we'll have a file system, which we'll verify. And then connected through a CAN bus, there's a second board, the control board. And this, if you like, is a cerebellum on the system. It contains the low-level software that basically keeps the thing flying. So controls the engines, etc. And it runs on a processor without virtual memory, an ARM M4, and we are building a verified RTOS for that. So this is a very small real-time operating system, actually just a few hundred lines of code, which doesn't support memory protection or dual mode execution. What does verification mean in this context? Well, in order to prove anything about the system, we of course have to assume integrity is maintained. And so we use static analysis to ensure that anything running on top does not interfere with the memory data structures of the RTOS. And yeah, there's basically the low-level software. A lot of that software will be actually produced by synthesis by Galois from high-level specs. And the approach we are using for being able to verify the overall safety properties is, as I said, based heavily on componentization. So we have our overall software structured into a set of components, and we have an architecture specification which is written in an architecture description language which describes the component structure of the system. So it's a formal language which describes what components there are, which ones are trusted, what the functionality of the expected functionality of the trusted components is, how they interact with the apps, with the untrusted components. And also in this high-level specification, there will be a specification of the safety requirements of the system. And the idea is that using basically model checking, we can, from this formal specification of the component structure, verify that assuming the trusted components behave as specified, the overall system will have the desired, will meet the safety requirements. This is still a bit hand-wavy. People are working on that, but it's very early days, that bit. But there's a reasonable degree of optimism that it works. It basically leverages security patterns which we build into this component structure, and for which we, for each pattern, specifically prove what security properties it has. And then the problem of ensuring or proving that the overall safety requirements are satisfied should be simplified. Okay, so that's the high-level view. And of course, that needs to map down to actual code and proofs that link up with the formal model of SEL4. There's a number of points to that. One is the glue code. So we have different components, they interact, and they interact via high-level abstracts like ports and channels, etc. And these need to be mapped onto the fundamental low-level SEO4 mechanisms, which are way too low-level to bother programmers with. And this is done by glue code, so basically code that is specified implicitly through this component description and really is basically a bit of a layer around L4 system calls. And this kind of glue code from that component model is fairly straightforward to automatically generate. But the point is, of course, because this is all described in a semantically rich language, when we can generate this code, we should be able to generate the proofs of its correctness. The generation works already. The generation of the glue code proofs is reasonably advanced, but not at the point where I can say it actually works. Hopefully within the next half a year or so, we will be able to generate verified glue code. And of course, that's one of the important inputs here. The second one is obviously the proofs of SEO4 correct, SEO4's properties itself, which we already have. And then we also need the correctness of the various trusted components. And the idea is some of these will be manually verified, but as much as possible, we want to automate that as well. And this is basically using synthesis and code generation. And I will talk about that next. So how we use synthesis and generation from high-level languages to produce this verified code. One example of these trusted components is device drivers. Turns out in a microkernel-based system, you don't actually have to trust most device drivers, because device drivers, they're all at user level. They don't run in the kernel. So they're subject to the same protection boundaries enforced on any application software. And that significantly reduces the pain with device drivers. However, there's inevitably devices which are critical. In our system, for example, we need the two boards talk via CAN bus, and we need to trust the drivers for the CAN nodes. And there's a few other devices which are critical. So we definitely need some trusted devices and therefore trusted device drivers. And what we're doing there is, in order to make them trustworthy, is using synthesis. And we've actually done that for the synthesis itself. We've done a while ago. It was published first 4 years ago. So the idea is, what is a device driver? It's a piece of code that mediates between an operating system interface and a device interface. The operating system says, I want to send this packet on the network. And the device interface says, if you write a 1 to this register and there's a value of 15 in the other register, then it will grab this amount of data from the address pointed to by that register and send it on the network. And what the device driver needs to do is translate these high-level operating system commands in this low-level read and write operations on device registers. And normally that's done manually. And the idea is, if we can formalize these interfaces, then it should be possible to do that automatically. And that's exactly what we've done 4 years ago, but that was very much a prototype. But it's not bad. It actually allows us already to produce drivers, synthesized drivers for a reasonable set of devices. So the most complex one is this ePro 1000. That's a gigabit Ethernet driver. So that's a reasonably complex devices of which you have lots of them. At the moment, the device driver is not functionally completely correct, but enough for our purposes. So we actually know how to synthesize device drivers. The two questions is, A, we'd like to have correctness proof. But of course, if you synthesize code, then you should be able to prove that the synthesis is correct. And this is one of the projects we're working on. But the more critical issue actually for devices is, where the hell do you get this formal spec from? For anyone who's ever written a device driver, has anyone ever written a device driver? A few people have. What do you do? Where do you get your spec from? Hey? Datasheet? Yes, either datasheets or you reverse engineer an existing Linux driver. Both are equally bad, because the datasheets are written by electrical engineers who have no interest and usually not a lot of clue of software, and they did the devices, and they first do the device, and when they're finished, then the manager tells them, now you have to write a data sheet, and by the way, we ship tomorrow, and they write something up which is typically hugely wrong. It's incomplete, it's buggy, and it's inconsistent, everything. So that's a very bad starting point for producing correct drivers. It's basically a guarantee for producing incorrect drivers. But in reality, this is how all drivers are written. And at the moment, we're doing the same thing. We take the data sheet, we formalize it in a state machine formalization and feed that into the device synthesis. So we'll still produce better driver than the manual driver writer because we introduce no new bugs, but of course they're based on the faulty interface specification. How do you deal with that? The only sane way to do that is by extracting the specification directly from the device design workflow. And this is how these devices get designed in industry. They start off with an informal specification, and from that they develop a high-level, semi-formal or formal model, and then that gets translated into what is called a register transfer level description, which is really the low-level state machine-based description of what the device does. And then there's automatic tools which generate the netlist, which is the silicon layout from that. So ideally, we would extract the device spec from this register transfer level description. Problem is, this is very low level and overly specific and contains a lot of information that is totally irrelevant for the driver writer, like exact timings, etc. Important for getting the device right, but irrelevant for getting the driver right. So the challenge here is to abstract the right information out from this RTL description, which at the moment we're putting in the too hard basket. We think it's solvable, but it's not solvable at the moment. Turns out that Intel is actually working on using formal methods to show that the register transfer level is actually a correct translation from the high-level model. And so what we're focusing on using this high-level model for extracting our device specification. And if Intel do that, Intel's internal project is successful, then we'll actually be able to produce device drivers that are really correct. And this whole project, the synthesis project, is a very close collaboration with Intel. Yes?
Model, what kind of formalism? It's System C. It's what it is.
Yeah, they use System C, and what's the other thing that's widely used? Yeah, this kind of formalisms. Okay, so basically, this is what we are working on at the moment in close collaboration with Intel, making device driver synthesis work well for real-world devices using actually trustworthy specification of the hardware interface. And the second example of generation of proofs or automatic verification of code is file systems, and this is a project we started about a year ago. And it basically, file system is a representative of lots of system code. And actually, it's a very important part of system code. So if you look at a typical operating system, Windows or Linux, about 80 or 90% of the code is device drivers. So that's the biggest chunk. And we have a story for that. It's not complete yet, but we're working on it. The rest is, most of it is two things. It's either network stacks or file systems. And file systems is the bigger part. So, and turns out network stack, synthesis of network stacks is actually been done. And there's a company called Kestrel in California where you can buy that. So we're tackling file system, and if we solve that one, then basically we can pretty much generate operating systems. And it's also representative of a lot of other system code, so more high-level stuff. One of the interesting properties which help us is file systems, by their nature, have well-defined abstraction layers. And between each of, these are basically defined by the operating system structure. And between each of these layers, the translation of functionality is actually fairly straightforward. Every decent undergraduate student can write an implementation like that. And if every decent undergraduate student can do it, we should be able to do it with synthesis or generation. That's the basic idea. And it also helps that the file system functionality at each layer is actually highly modularized, which again helps. So this is the basic idea. We operate at a component level, the file system component level, and produce formal specifications of each of these components. And you do these in domain-specific languages that allow us then to synthesize or generate, it's not really synthesis, it's generation, both the formal specifications of the components, the implementation, as well as the correctness proof. So generate both the code and the correctness proofs of all of these components. And then have a manual step where the overall file system specification is refined into these component specifications. And that's done manually. And this is the framework we're building at the moment. A position paper on that has just been accepted for the PLOS workshop. The idea is we actually have two families of domain-specific languages. The one is called the data description language, which describes the data structures both on medium as well as in memory, and the transformation between them. And then there's the control, and there's a typo which I always forget to remove. It's supposed to be CDSL for control domain-specific language, which describes the algorithm. And the whole point about the file system is these algorithms, they're sort of the interesting bits, but they're not very complicated. They're relatively easy to write down typically, and therefore easy to automatically implement. So what the framework does is we specify the data layout in this domain-specific language, and from that synthesize mostly the conversion code between the rich in-memory data structures and the serialized on-disk data structures. And we generate the spec, the code, and the proofs in between. Code generation already works, spec generation works, sort of, and I'm still waiting to see the first generated proofs, and the team promised me by the time of the PLOS workshop, early November, it will be there. What we also then generate trivially is declarations of the functions which need to be used by the control specification. And then this gets used by this control domain-specific language to define the actual file system algorithm. And the idea is, again, to generate the spec, the code, and the proof in between. And then we have the overall functional specification of the file system itself, and refine this into the various specification of the control code, the serialization code, and some general purpose abstract data types which are independent of the specific file system. So these are the B trees and the inodes and all that sort of stuff. And of course, file systems in their high-level functionality don't differ very much. Different file systems, the reason there's 40 or 50 file systems in Linux is they talk to different media. So this is here. They have different robustness guarantees, like how resilient they are against, say, hardware errors and all that sort of stuff. But the top-level functionality is not very different. So I expect that a lot of this functional specification here and also the refinement proofs down to the component specification will be highly reusable between file systems. But at the moment, that's an unproven hope. So this will keep us busy for another 2 years, I expect. We're trying it out on a prototype which is, okay, I've gone through all that, which is a Linux compatible flash file system, and we don't go the whole stack at the moment, but we anchored between the virtual file system layer and base it onto a flash abstraction layer, so we don't deal with wear leveling and all that stuff at the moment. But it's basically sort of the interesting bits of the file system. Okay. So, this sort of gets me where we really want to end up, and this is building full-scale systems where we prove correct all the critical bits. And that requires a lot of system, which we either have or are on the way there. So we've got our verified microkernel. We got partially verified resource management. This is really mostly falls out of our architecture description language specification and some prior work we've done on reasoning about rights distribution and system. We're working on verified device drivers. We're working on, I've actually got some animations for this. We're working on verified file systems. Some other people are doing verified software stacks. And then the idea is, okay, there's then some application-specific functionality, which of course needs to be verified as well. This can, in general, this will probably be done manually, although domain-specific languages may help there as well. The hope, of course, is that this doesn't have to be done in C, but should be done in a better environment, a high-level language that's memory and type safe. And so we have another sort of almost a skunkworks project at the moment. Actually, we're working with Tony Hoskin from Purdue on this, on verifying a runtime system for high-level language. At the moment, we don't know which high-level language, so we're working on a concurrent garbage collector, which is a necessary part for any of these type and memory-safe languages. My feeling is a good candidate for such a language could be Google Go, because it's got some good properties. It's a small language and therefore doesn't need a big runtime system. And for us, of course, that's a massive advantage. It's also, its syntax is C-based, but its system model is very Ada-like. And of course, people working in critical systems, a lot of them like Ada, so I can see this as a potential Ada killer. The whole point is having some language where a lot of the pain of C is taken out already by restricting the language constructs, making it type and memory safe, and then being able, once we have a verified runtime for such a language, it means that we could do verification at the level of the semantics of this high-level programming language, where of course it's much easier. So the overall lessons we learned so far from this project is the claim that formal methods are expensive is no longer necessarily true. I grant that we have a bit specific environment. We have excellent formal methods people, which are of course underpaid by industry standards. But we're working towards making it more approachable by mechanizing a lot of it, using synthesis and domain-specific languages. And we really think that we can scale this up, as I said, factor of 2 in cost and factor of 10 in the amount of code using synthesis and high-level languages. And I really think we are at the point where there's going to be a real phase change in the way people build systems. I think we're really at the point where we can show that it's the wrong approach, just looking at the cost to build systems the old-fashioned way, and we will see that over the next 5 years. And I reckon the next 5 years will be incredibly exciting. Thank you.
Let's take questions.
So, according to the literature, the horrible thing about file system is not the proving that they're doing the correct operation, but that they keep a consistent state even though they crash. For example, loss of power. And so, do you think you can still prove that no matter where your file system crashes, it still keeps its coherency?
Yeah, this is actually one of the keys to making this approach attractive. Because if you look at file system code, a lot of it is error handling. Basically, you try an operation, it fails for some reason, typically having to do with availability of hardware resources or sometimes failures in the hardware, and then you have to unwind. And so there's file system modules where literally 80% of the code is attempt blah, if fail, roll back. And that code is logically really trivial, but it's tedious and it's very error prone because it's very easy to roll back too much or too little and all that stuff. It's perfect for synthesis. This is actually where we get the biggest productivity gain we expect, is by hiding all this recovery stuff under the hood of the domain-specific language.
And last thing, if you have to plot a percentage of how far you are from a Class A avionics certification, what would be your number?
That's a bit difficult to say because they look at lots of other stuff, right? And at the moment, the way this certification works is they don't really give enough credit for formal verification, which still have to do a lot of documentation and process shit, etc., which of course is completely pointless. So I wouldn't want to attempt it until they fix their certification regimes.
Until they change the certification standards.
Yes, yep. Yes. And of course they're moving that way, right? Herring, B, C, D, they're increasingly deploying formal methods, but they haven't really got to the point where it would be worthwhile for us to go through it. Of course, if someone wants to use it in aerospace, which I hope it will happen sooner or later, then they will have to go through that, but that's their problem then. So I'm very happy to help Airbus doing this.
More
Thanks.
questions? Yes.
So, Gernot, you had some numbers from industry about the density of bugs and so the occurrence of failures and vulnerabilities in software. There must be, I'm assuming, similar numbers concerning hardware. Are you aware of them?
Hardware is actually... So it's very difficult to get actual numbers on hardware failures. Intuitively, you would think that that there is a significant amount of hidden hardware failures. Turns out it's actually not the case. At the moment, the industry is still extremely good in not preventing but detecting hardware failures, for example, resulting from single event upsets and stuff like that. So the best I could do is talk to people in Google, and I got some informal information out of them which shows that the number of unhandled hardware failures, which is hardware failures they see at the software as incorrect behavior of the hardware, is still very small compared to the fail-stop failure, which basically means the hardware detects there's something going wrong and it forces you to reboot the system. So at the moment, they're very good in at least detecting those and protecting you from them in that way. The question is how much longer this will be possible, because with shrinking miniaturization, the reliability, the inherent reliability of the hardware is inherently decreasing. And the question is, how long can people afford to... There's a significant cost, of course, to maintain, to checking for all this consistency and detecting those things. And when they will start just giving up and giving us unreliable processors, which, of course, creates a whole different kind of game. And we're actually working on that. So there's my colleague Kevin and one of his PhD students. They are working on running the kernel in a redundant configuration across multiple cores, where every kernel operation is done on 3 cores in parallel and only made available to the outside when all the cores agree. And it's interesting games you have to play there with devices, etc., to make this work. But in principle, it's possible to deal with that, of course, through replication.
But would you have to do for the hardware a process parallel to what you're doing for the software here to actually give me a system that's truly trustworthy? I mean, in addition to errors that are inadvertently brought in, we have to be aware of the fact that for all we know, the NSA is doing things to NTASS design. I mean, how do you deal with that?
Yeah, it's obviously not a problem we can deal with. If people build backdoors into the hardware, then we're obviously subject to what the hardware does. It is a real... I was actually at the meeting just on Tuesday at the BSI, the German Federal Office for Information Security, and they worry about these things a fair bit. And I don't really see any way in the medium term any alternative to just having trusted hardware suppliers. Because, yeah, I mean, someone who controls the production of the hardware can, of course, put in unspecified functionality which you can exploit, and there's nothing the operating system can do about that.
Okay, more questions? Yes.
Can you please comment on the runtimes of different components of the toolchain, specifically the SAC-based equivalents?
Okay. So the complete binary verification of the kernel from memory takes about 4 days to run, roughly. The actual refinement proofs for the C-level verification of the kernel, they run overnight. They're part of our regular regression suite. We just run them each night. And there's a board that shows how many proofs break, and in the morning someone has to fix them.
More questions? Okay, so let's stop here. Thank the speaker.